I thought from the beginning, at the risk of stating the obvious, it might be worth just explaining the background to the term HCE, because I don't know who's in the audience. So let me do that, and it kind of leads into my presentation anyway. So HCE stands for Host Card Emulation, and the origin of that term is card emulation, and the idea being that you want your phone to behave like a card. So I said it was going to be obvious, so that's kind of a pretty sort of dumb explanation. And the point I'm making is, particularly with payments, when we talk about card emulation, what we're saying is we want the phone to appear to the point of sale terminal precisely as a contactless card. The point of sale terminal can't distinguish between your card and your mobile phone. So that's what we mean by card emulation. And by host card emulation, what we're saying is, instead of doing that in the secure element, in the sort of secure piece of hardware inside the phone, we're moving it out into the host operating system. The reason I'm kind of labouring this point is there have been articles in the press which have referred to the host as the cloud service. That's not what the host in host card emulation means. The host in host card emulation is referring to the mobile operating system, Android or BlackBerry. And actually, just to pick up on a point from the previous presentation, HCE is supported in BlackBerry already and has been for some time, although obviously BlackBerry is a much less significant platform these days. So what I wanted to do this morning, I'll skip over that, is I'm going to have quite a payments focus, but because what we're talking about here is how to emulate card transactions in a phone, and in particular in the host operating system, the right place to start is contactless transactions. So I'm going to have a briefly look at contactless transactions, what they are, and my focus is security as well. So look at what they are, where the security is, and then show what changes between there and normal NFC, where you use the secure element, then move into HCE and show how that introduces some kind of security gaps. And then we'll have a think about what are some of the emerging technologies that may help us to address some of those gaps. So my objective really is to say, explain what HCE is, and then think about some of the tools that we might use, some of it including the secure element, some of it not including the secure element, to help us make these payments work. So this diagram here is a very dumbed down picture of a contactless payment. So you've got a contactless card. Inside that card there are some secret keys that perform a couple of functions. Firstly, the card needs to be able to demonstrate to the issuer of the card, that the card is genuine, and it does that using some shared keys, DES-based shared keys, so, symmetric keys. So when the card sends a transaction to the terminal, it's signing a cryptogram with that shared key, which passes through the payment network to the issuer, and the issuer can go, yeah, the issuer knows that key and can check that the cryptogram is correct. The other key that sits on the card is a private key. By that I mean it's an asymmetric key, so there's a private key, and the terminal actually has a public key associated with the card scheme, so it will have a MasterCard or a Visa or an American Express key in there, and the card says that the card will sign a challenge for the terminal. With it is a certificate, and the terminal can check the certificate's valid, it can check the signed challenge is valid, and determine that the card is indeed genuine, which is particularly important in offline transactions where the terminal is not going online to the issuer. And it's also important in transit, in the open loop payments on Transport for London, for example, where there's a delayed auth. So you want to determine that the card is genuine because you're not actually going to submit the payment to the issuer for authorization until sometime later. A couple of things to say about contactless payments. Firstly, in the way that I've described it here and in the main usage at the moment, there's no cardholder authentication, so there's no facility for entering a PIN, certainly in an offline PIN market. In an online PIN market where you can put the PIN in on the terminal, that's different. But in the UK, it's the case that there's no facility for doing, or no obvious way of doing cardholder authentication, cardholder verification. The second thing to say is that card, especially if it's a a contactless only card, so for example the Barclaycard pay tag sticker is an example of a contactless only card, you have no way of managing the risk parameters inside that card that control its usage. So for example, there might be some limits about the amounts that you can spend. You have no way of managing those remotely because there's no interface for doing that. With a contact card, you can script to the card. When you put the card into a terminal, it's in the terminal long enough that you can send some management commands down to that card. But in the course of a contactless transaction, which is typically only a few hundred milliseconds, there's insufficient time to do that. And yeah, I think that's probably enough because I want to get onto the HCE bit. So that's contactless cards. So what happens when we move that into NFC, normal conventional NFC with a secure element? So you can see instead of having the card here, a smart card, I've now got another smart card, which is the SIM. Same keys are in that card, so it works in exactly the same way from a payment point of view. But there's a couple of key differences. The first thing is the mobile phone has a user interface, so you can do a passcode entry. So whereas before you might have wanted to limit the value of transactions that you would do with a contactless card because you can't authenticate the user. And then the other thing is you can have something like a mobile gateway, a server-side component that can communicate with the phone over the wireless network, over the mobile network, or over Wi-Fi or whatever, and manage some of those parameters in the secure element that previously you weren't able to do. So moving to mobile-based NFC, secure element-based NFC on a mobile, adds some distinct benefits in terms of the normal management of that payment product, aside from all the other potential marketing benefits and everything else that people are trying to do with NFC. So the question then becomes, and we've heard a little bit this morning about some of the challenges with that NFC ecosystem, the fact that it was very complex, some of the commercials were kind of difficult to negotiate, so it hasn't really taken off, certainly not in this market. In some markets, so for example in China, there's some quite big rollouts of secure element-based NFC going on, and in some European markets as well. But in some places it has been quite a challenge to get the banks and the operators to work together and to find ways that work viably. So the question is, what happens if you get rid of the secure element altogether? So what happens if the secure element, and so the first step in this process, and this is where HCE kind of started out a couple of years ago, was to think about putting the secure element in the cloud. So the idea is you take those keys, the keys that previously were protected in this secure thing within the phone, and you put them in the cloud. So you put them in a data center, a secure data center. The keys are held in an HSM. It's all really, really robust and secure. So is that good enough? Does that solve the problem? And that's actually where the HCE conversation kind of started. And actually, there's some issues with this. So the first thing is, how are you going to do your cardholder verification that we just introduced as one of the benefits of having a secure element? Because actually what's happening here is, it's no longer the case that you're just authenticating yourself into something local in the device. You're now doing an authentication to the cloud. That cloud is going to be a service on the web, on the internet, so anyone can get access to that. There's quite a big attack surface for that cloud. So authentication to the cloud is a key problem. Second problem is performance. So if the terminal is wanting to request to the phone to do a transaction, but the phone's got to go back to the cloud to generate the cryptograms or whatever, or to sign a challenge, and then come back to the terminal, that's just not going to happen within the sort of few hundred milliseconds that we're talking about. The latency there is going to be too great. And then the third thing is, if the phone is out of coverage, then the transaction won't work anyway, because the phone won't be able to access its secure element in the cloud. So that clearly doesn't work as a model, but it's where we started with HCE. And if you weren't worried about performance and you could guarantee the phone was always online, then that kind of would possibly work. So what you might do to then move that forward. So we still want to keep the keys, probably the valuable keys, the keys that are associated with the account in the cloud. But maybe what we can do instead is say, well, let's give the phone a key that's valid for one transaction. So at the moment, the model that we come from in card payments is you issue a card, and in that card you put keys in it that are going to be valid for 3 years. those are quite valuable keys. If you can get hold of those, potentially you've got 3 years worth of transactions. I mean, the card might get blocked, but aside from that, they're quite valuable keys if you can get hold of them. So instead of doing that, let's have keys that are only valid for 1 transaction or for a day's worth of transactions. Then you've immediately limited the scope of those keys. Because those keys are less valuable, perhaps we can accept lower levels of security around the protection of those keys. And that's one of the key things that that HCE is kind of looking at, is saying, well, okay, can we manage the risk in other ways rather than have the secure element? But the important thing to say here is that the overall kind of security paradigm, the way that we're used to managing security, has changed. We're moving from something where it's kind of deterministic. We know what the piece of hardware is. We can have that certified to a very high level. We're moving away from that to a much more kind of risk-based model, which is quite a significant mindset change particularly for banks probably used to issuing cards. So having thrown the secure element away, where might the security be needed? So in this diagram here, what I've tried to do is thinking about these kind of light-coloured boxes here are meant to represent the information assets that we're protecting within the mobile payment application. And there's kind of, broadly speaking, 4 different things. There's general configuration data, so general business data about how the application works. There's limits, so things that control the risk parameters around the payment transaction, how many transactions you can do, the value of transactions, those kind of things. There's secrets, so by that I mean those limited use keys, or indeed pins that you're storing locally to verify the card holder. And then there's the software itself. The software itself is quite important, because if the software can be compromised and changed, potentially you can subvert the application. So there's four primary areas of 4 primary assets that we're trying to protect, and then there's 4 areas that we need to four things that we need to think about. So there's the storage of those things. How do we store them securely on the device? And then there's secure processing. When we use them, how do we make sure that, so in particular the keys is a really kind of instructive example here. So if I have a cryptographic key, I can store it securely somewhere, perhaps, but then when I run the cryptographic process, when I actually do the encryption or the decryption or the signing, whatever, that key then comes into memory, and if someone can interrogate that memory, they might be able to lift the key out of the memory. So the actual processing is important as well. And that's kind of the security, sort of areas of security need within the device. And then obviously this device is going to be communicating to the cloud, to the issuer, to the management system in the bank. There's a need to think about authentication. So firstly, how does the cloud know that this is the correct device, that it's the correct user, that the app's correct, that those 3 are a valid combination, all those sorts of things. And actually it's the other way around as well. How does the device know that it's connecting to the correct issuer and not to some spurious site that's trying to fish details? Equally important. And then across those 2, how do you, in those communications, how do you make them secure, so that you can't have a man in the middle or someone compromise the delivery of that information from the cloud into the device so that it can then perform a transaction. And a comment to make here is that there's not one size fits all. I'm just going to put up some of the technologies that may help with solving some of these problems. The point about these technologies is, 1, a lot of them are not mature. 2, a lot of them are not available on every single handset. And so what that means is that 3, it's not one size fits all. If you're looking to deploy a payment application, or in fact any application, but I'm thinking about payments particularly here, to a device that's going to use HCE, then for the moment, potentially you need to think about doing different things or different devices, or having in your device management the ability to think about, to distinguish between what the device is, what its capabilities are. So whistle stop tool then. Secure element we just heard a lot about, so I won't dwell on that in detail, but clearly the secure element can help a lot in providing security. The way that I see the secure element working is not being used in the way that we're used to, with secure element NFC. So we're not talking about each bank needing to issue their own application into a secure element with their own security domain, because then we just go back to where we were. I think what could work would be if the secure element owners produced some kind of native generic cryptographic functions that anyone could use, a kind of an open API. There is an example of this in the marketplace, which we'll come on to in a second. It doesn't use a secure element, it uses a TEE. It's the Android key store, which can be hardware backed. In that case, you have a model where there's a service there that's available in your phone. It's a TEE, and I'll explain what that is in a second, but it's like a secure element, and you can do some sort of fairly primitive cryptographic things, but you can use those as a basis. They provide you kind of a secure anchor for doing the cryptographic piece of your transaction. And one of the things that I think with secure element, normal, conventional, traditional secure element NFC, one of the things that we had was, in the secure element we put everything. We put the cryptographic processing, we put the business logic, everything about the payment all goes in there. Well, we don't need to do that. Let's extract out the things that are really important, the things that have to be done in a secure element, and put them in a secure element, and everything else, we can let run in the host, and it uses, so it will use this feature. Now, obviously, for this to work, there needs to be an appropriate business model in place. I know that GSMA, for example, are looking at this kind of stuff, and it needs to be, priced appropriately so that people would use it. But this is technically, this would be a sensible approach. So I mentioned TEE. So a TEE is like a secure element, but without the tamper resistance. So there's a thing called Trust Zone that ARM will produce the specifications for lots of chips that go into mobile phones. And in their specifications for quite some time, there's been this concept of a thing called Trust Zone, which is at the hardware level a separate secure OS. And when your device boots up, it boots up the normal OS, Android for example, and then you have a secure OS, which is completely separate and independent from Android, and it's separated in the hardware. So it's very similar to a secure element. And in fact, to provision an application into the TEE, a custom application into the TEE, you need to speak to the owner of the TEE. So, for example, Samsung Knox Samsung Knox is the Samsung's TEE on their devices. If you want to put a custom application into the TEE, you need to speak to them because they have the keys that protect that area in the same way that a secure element owner would have the keys to protect a secure element. So that kind of doesn't help, maybe. But because then we're back in the same situation of having to negotiate and pay a third party. However, the TEE, it is being rolled out on numbers of devices. So several Samsung devices have Samsung Knox as part of the standard, image for their, or standard sort of configuration for their devices. And one of the things that it is being used for that I've just mentioned already. Let's skip forward. I know, hang on there. Is about is the Android key store. So if you have an Android device, in Android there's a thing called the key store. It may or may not be hardware backed depending on the capability of the device. But if it is, then you know that your keys then are being held and processed in a area that's separate from a hardware point of view to the main operating system. It's not tamper resistant in the same way that a secure element is, but it does provide some level of security. There are some issues with the Android key store that I don't have time to talk about. I can talk to people about it later. It's quite immature, but it's developing, and I think it's something to look at in the future. So there are some known bugs and defects and things. I mean, I could explain to people offline how to subvert it, if you want to know. But it's a step in the right direction. The other thing I probably quickly ought to talk about is white box crypto, which is being mentioned a lot in conversations around HCE as an alternative to hardware cryptography. Secure element is what we call a black box cryptography. So the point about a secure element is The key is secret, but also the processing of the cryptographic algorithm is done in a secret, enclosed environment. You can't observe the cryptographic processing, because if you could, you'd be able to see the key. Now, move that into a pure software environment, we have to assume that the memory can be interrogated and observed. So that's not a black box environment. So what do we do instead? What white box crypto does is it breaks up the algorithm, DES. It works for symmetric algorithms only. And whereas previously your algorithm might be a loop that just kind of goes round numerous times saying, do this operation, do it again, do it again, do it again, and in the process scrambling the data. What white box crypto does is it breaks that up, so you have a piece of code which is the first time around the loop, then another piece of code which is the second time around the loop, and so on. And into each of those pieces of code, you insert some information that's kind of related to the key. You can't recover the key from it, but the point being, you end up with a piece of code that if you observe that piece of code running in memory, you cannot determine the key. The key never gets revealed in memory. So what that means is you've got an implementation of a DES encryption, for example, that you can observe and you don't get the key. So that's kind of interesting. There's a couple of problems with white box crypto. Nothing's ever simple. So the first thing is the process of implementing it means that your code balloons, because whereas previously you've got a nice loop that just goes, you've now got a piece of code where you've got each iteration of that loop is a separate piece of code. So you can imagine the code gets quite big. The second thing is each white box crypto implementation is for one key and one operation. But what I mean is it's for a key for encryption. If you want to do the same key for decryption, different white box. If you want to do a different key for encryption, different white box. So that means that the idea that we're going to have limited use keys and delivering those for every transaction to a device, that becomes a little bit impractical, because the task of delivering large amounts of data, possibly megabytes of data down to the device for every transaction is just not, it doesn't work. However, I think potentially as a device that doesn't have a secure element or a hardware-backed key store, potentially you could use this as something better than just normal OS storage, or better than obfuscation on the OS, for storing a static key that you use for authenticating the device back to the cloud. So it does have potential uses. And the other thing to say that's really important is if you can grab the whole white box, the whole bit of code, and lift it onto another device, then effectively you've taken the key. So there are some weaknesses there as well. But it's something that's being spoken about a lot, so you need to be aware of it in terms of possible HCE implementations. FIDO I don't have time to talk about, but this is really important, and it's about how you authenticate. The good example here is Apple Pay, where you use your fingerprint. You put your fingerprint on the fingerprint sensor, and that authenticates the user. Well, FIDO is an infrastructure or a set of standards that are being put in place to enable primarily authentication from the mobile device to online services, and I think could be particularly useful in terms of if you've got your HCE application authenticating you to the cloud to then download the keys. But I'm happy to talk about that afterwards, but I think we're out of time. So my last slide, as we look at all of this stuff, it's quite immature, there's lots of things to think about, but when you think about authentication, or when you think about security, particularly with a payment application, you'll be dealing with a device, so you're wanting to put keys onto a device to enable a transaction. You'll have different levels of trust in that device depending on its capabilities. The user may or may not have been authenticated to some level, and then the application as well. I haven't talked at all really about application, how well you trust the application, or I also didn't mention things like devices being rooted. So on those three axes, the user, device, and that app, you're going to need to make some kind of judgment, and the likelihood is that there will be a need to adopt some kind of graduated scale of security and risk, particularly if you want to launch an HCE application onto a whole range of different devices, because every device is different. And so I think we probably need to be thinking about when all those three things come together and you combine them together and they give you enough confidence, then maybe go for something high value. But other times, you know, the risk might be too high, so you have to go for low value, only support low value transactions. So this is a change of mindset for card issuers. It's no longer a case of thinking about low value and high value, or card present and non-card card not present. There's going to be some kind of graduated scale, I think, potentially.